Hey everybody, let's get ready for simple harmonic motion number 2. So I'm going to try to focus in on some of the notes that I've made on the questions. Alright, so number 1 is about a seconds pendulum. This is a really straightforward question without a whole lot of trickery or anything like that. All you're really being asked to do is to find the ratio of the free fall accelerations at the two locations. And you know, they're going to be awfully close to 1, but you know, go out a bunch of decimal places there, and you're just simply going to use the relationship for pendulums that you see up there. It's really not that big of a deal. Okay, number two. Simple pendulum has a mass of 0.650 or whatever yours will say. Let me steady myself here, sorry. And you're given an angle, it's being released. Solve this problem by using simple harmonic motion model for the motion of the problem. Now, truth be told, you have two possible ways you can go about solving this. You can use simple harmonic motion, which would be, you know, the v equals negative omega a, acceleration equals negative omega squared a. You can also work with torque as well. I have some key things jotted down here for you. Remembering what omega squared means for a pendulum, the fact that it's G on L is a helpful thing to note. And you know, if you are going to be using the small angle approximation, you should, you know, consider what theta really means. Well, honestly, I mean theta and R, or I'm sorry, arc length and amplitude, or what am I saying here? Yeah, they should be about the same, right? That's what our small angle approximation is all about, that our arc length, or sine theta, is actually equal to theta. Not so bad. So we're going to use that small angle approximation so that our arc length and our x, when we're dealing with, you know, displacement, that could be, those should be the same with a small angle approximation. Main thing to consider though, make sure that you have everything in radians if you're going to take this route. That is kind of important. Gives you a way to find amplitude here by using r theta equaling a. If you're going to look at torque, do keep in mind what we're talking about there, that the torque is being caused by the sine component of gravity as the force, and the length of your pendulum is going to be your radius. And if you consider that to be torque, remember torque is also equal to inertia times angular acceleration, and that the inertia we'd be dealing with is for a point mass. So we'd be dealing with inertia being mr squared. So you've got a couple possibilities there that you can go about solving for maximum angular acceleration. Maybe you find the linear and then you convert it to angular using the radius. Or perhaps you just, you know, solve for it with torque. It's totally up to you how you want to do that. Okay, number 3, angular position of a pendulum and so forth. Okay, so the angular position of a pendulum is represented by your equation. You're given your equation. Determine period and length. Oh, that's not so tough. Okay, so we should be able to, yeah, gosh, they give you everything you need right there. Just go ahead and plug and chug. You should be good to go with the relationships that we've got jotted down here for you. Okay, now number 4. Number 4, they start trying, I don't want to say trick you a little bit, but they are making you think a little bit differently. Remember the whole net equation thing that you're dealing with. All right, if we're finding period of a pendulum, it's a relationship with L on G. Just realize that if that's really the acceleration they're talking about, assuming there's nothing else happening, it would just be little g. If you've got something else going on, like this elevator or this truck accelerating horizontally, well then your acceleration isn't going to be g. There's going to be something else going on there. So the whole accelerating upward elevator, that's a key thing to remember. You know, that you've got a tension going up and gravity going down, and which one is bigger, and then so what would your acceleration truly be, so that you can then find, you know, once you know the acceleration, you can then plug it into that equation. If you're dealing with accelerating downward, well then Fg is going to be bigger than t, right? So you're going to need to again find the real acceleration. And when you're going horizontally, remember you've got two accelerations. One is going to be in the x plane and one is going to be in the y. So you're going to need to use the Pythagorean theorem to find the resulting acceleration, and you can use that to find the period. Okay, so do keep that in mind as you're going there. It's not really a whole lot different than, well, I shouldn't say there's anything terrifically simple harmonic about it, with the exception of finding the period. The rest of it is mostly, you know, it's forces. It's a review of forces. All right, our last one here is this big old chart. And gosh, this really shouldn't be tough, I hope, at all. You're given the length, you're asked to find the period, you're asked to find little g. And but do keep in mind that there is a part C here that talks about doing a graph. And if you didn't see it in the instructions, I do not want a graph from you. No, 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 no. All right, so don't do that. All right, do keep in mind that you're given the number of oscillations in this question. You are given the lengths and the total times for the number of oscillations, whatever random number they give you there for your oscillations. And you're going to determine the period for each of the lengths. So yeah, it's super simple, I think. If you're given the number of oscillations and the time, finding the period is simple division, and then you can use the relationship you already know to find the second value, which is the value for little g. As you can see, I'm kind of cut off here. All right, so hopefully that is enough to kind of get you going, and let me know if you have questions.